Okay, great. So first up, thanks very much for giving up your Thursday evening tonight to come and hear us all present. It's really, really appreciated. So yeah, thanks so much for organising us, for inviting everyone along, and for coming along and listening to our presentations tonight. So I'm here to tell you all about my research into the future of drinking water, into chemical-free drinking water treatment and distribution. So let's get going. So who am I and why am I talking to you today? So yes, my name is Natalie Lam. Literally last week I started my first adulty job. So yeah, at the end of this month, for the first ever time, I'm going to be paying taxes. So kind of nerdy, but I'm super excited about it. And what I'm here to talk to you about today is my PhD research with the University of Sheffield. So I've spent sort of the last 4 years. I've just only submitted my thesis and I'm waiting for my exam on the 19th of April. So it's all been about a PhD in civil engineering and microbiology. So I'm actually a microbiologist by background. Please don't sigh, please bear with me as I try my best to talk you through the civil engineering of my project that I've been doing, all about chemical-free water. So I'm going to be talking about
Natalie, apologies. If you're sharing your screen, I can only see your notes page rather than another one. I'm not sure if you're sharing on a separate one.
Okay, hold on, let me.
You want to maybe launch it?
I think it launches on a separate screen. I think that's what's happening.
Possible.
Oh, you've got it just changed there. If you go back one.
To this?
See if it changes.
No?
Yeah, so if it changes on your end, Natalie, it's because, do you have 2 screens?
No, I've only got 1 screen.
Okay, so it must be the share button. So when you press share screen, if you share your whole screen rather than the PowerPoint.
That's the one.
That's it. You got it.
Okay.
Do you want to flick back one slide? There you go. Yeah.
So this is my intro slide. This is who am I and some pictures of my face and sort of what my background is. Thanks so much for telling me that the technology was just completely breaking. Thanks so much. I would have just carried on, and I don't think I've even got any notes, so you would have had a very boring view. So yeah, today I'm going to be talking about how can we prepare for future challenges in water. Why did I bother doing this research for 4 years of my life? And is chemical-free water possible in the UK? So I want you to grab a piece of paper and a pen. So just have a look around you, grab what you can, use your phone if you need to. And I've got a bit of a question for you to answer. In today's drinking water pipes in the UK, what do you think is the longest time it takes for water to get from the water treatment works to the kitchen tap? So this is in the UK, and I want your best guess. And if you're feeling really brave, feel free to put it in the comment section of the chat. I promise I won't make fun of you, but no, I'm not saying anything about your colleagues. So yeah, what do you think? Do you think we're talking like minutes, hours, days? What do you reckon? So this is a question that I'm posing for you today. Give you a second to just jot down your answer. Best guesses. So in the UK, drinking water can actually take as long as 10 days to be transported from the water treatment works to your kitchen tap. So that's just like the maximum. Generally, you're looking at sort of between 3 days, sort of 5 days. I would say 3 as an average is pretty close to what we're talking about. But yeah, that's how long it takes for the water in the UK. So even if you've got the best water treatment possible, so you're talking about a water treatment plant, you've got maybe UV light, advanced oxidation processes, you've got some really cool, innovative technologies, a bit like a sci-fi film, out of the water treatment works. Because the water is sat in the pipes for this amount of time, it can really degrade the water quality. And the thing is, these pipes that we're talking about, you know, they can be corroded, they can be cast iron, and as well, you know, they can be really old. So we've got pipes sort of out of a Victorian era, sort of 100 years old pipes in the network. And so yeah, it can cause all sorts of problems with water quality. So to prevent this, what we do in the UK is we apply some different chemicals to help safeguard that water in its journey in the pipes. So these are chemicals that are not used at the water treatment works process at all. They're just used to try and protect it on its journey in the pipes, because we know how bad these pipes can be. So what does the future hold with water? So these chemicals that we're using, they work right now. We've got really good quality water in this country. We've got 99.95% compliance with really strict regulations over here. But the same might not be true in the future. So particularly things like population growth, and a real massive one for water is climate change, because climate change is going to really change the quality of the source water. So at the moment there might be a particular, say, river, and we're like, oh, that river's disgusting, we don't want to use that for drinking water. But in the future our standards might lower, because, you know, we might have to take on these challenges. We might see water bodies sort of depleting, and population growth. We're going to need more and more water in future. So these are just some of the future challenges that we've got in water in this country going forwards. So how can we prepare for these future challenges? So at the bottom there and on the right hand side, these are some technologies that I'm working with in my new job, and maybe when I get to know them a bit and I do some trials with water companies and stuff, I can come back in a few years' time and tell you all about them. But what I'm talking about today is the one on the left. That is my pipe testing facility. And so really, how do we prepare for these future challenges? We need to do future work today. So turning off the chemicals in this country, it's not something we're going to be doing tomorrow or next week. We're sort of looking at 50 years in the future here. So we really need to be doing that sort of really like blue skies thinking, that blue skies research, if we want to prepare for these future challenges that we've got. So why research chemical-free drinking water in particular? I've already said that water's compliant, the chemicals work, everything's up and running. Why would we want to mess with the system? Well, basically, the chemicals that we're using can have unintended consequences. So a really good example of this is we dose chlorine, so the same chlorine that's used in swimming pools, but in much lower doses. So we're dosing this chlorine, again, reminder, just to protect the water going through those pipe systems, not in the treatment works, just for the pipes. And the purpose of this chlorine is to make sure that microorganisms aren't able to grow and reproduce and survive in these pipe systems, because then you'll end up with really high numbers of microorganisms at the tap. But the problem with this is that microorganisms are surviving and they are entering the tap, even though we're dosing this chemical to try and stop it. There was a really interesting paper published last year by some people from my research group at the University of Sheffield, Fish, and she was really working all about this chlorine and the different doses. And what she actually found was when higher chlorine was dosed, microorganisms survived better. What we've actually found is chlorine doesn't necessarily reduce the numbers of microorganisms. What it does is changes the community of microorganisms. It selects for different species. And the real problem with this is that there's that potential for chlorine resistant microorganisms to be present in future. And that would be majorly concerning for us. It's not happened yet, but it's a risk. So going back to that whole perfect pipe network that I was talking about. So saying, you know, we've got these 100-year-old pipes, blah, 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 blah. What if we got rid of them all somehow, magically overnight, changed them all and made them be the best possible materials, like next generation materials, no leakage whatsoever? Could we switch off these chemicals? This is what my research was all about. So like I said, I'm not an engineer, I'm a microbiologist. So I pulled up PowerPoint, as you do, and I designed these systems on PowerPoint because I've got no sort of background in that kind of thing. We sent off these designs to a company called Boltings, who then actually produced them as proper designs. And then that got sent to Chemical Support Systems, who are a company based over in Chester, and then they actually manufactured these systems, all based on my PowerPoint drawings. So what they were is we had 2 identical shipping containers, and when you walked into these containers, there was a wall of pipe on the left and a wall of pipe on the right. And the left-hand side of the pipe there, it had chlorine and phosphate dosed. So those are 2 chemicals used to treat water. And on the right-hand side, they didn't have them dosed. So I was basically comparing these 2 identical pipe sections. I had one of these facilities at a surface water site. So surface water sites get their water from things like rivers, reservoirs. They're generally poorer quality water because it's like an open body of water, so anything can kind of get in there. And then I had one at a groundwater site, and with groundwater, it's been like filtered through rocks, through the ground for a period of many years. So it's generally higher quality. We're sort of abstracting it out like how we used to use wells. So here's a bit of pipe, because what woman doesn't have loads of bits of pipe in her flat? So yeah, it was made from grade PE100 HDPE pipe. So that's what I got built. Ran at around 0.7 litres per second. So if that's not the units of measurements that you use. Capacity of around 170 litres, and I was circulating for an average of 3 days. So the water would enter the pipe system, circulate around for 3 days, and then run to waste. That's very important. We run to waste. I wasn't trying to feed people this water, because at the end of the day, I was trying to see if we had this perfect pipe system and we got rid of the chemicals, are people going to die? That's basically what I was testing for. So how did I actually do this? So if you're in my pipe sections, I designed these like bits of removable pipe wall. So I've got a coupon here, which is you take the cap off and then you can see this coupon. It's a removable little section, so I get a toothbrush, very technical, brush off the material from the pipe wall and analyze what's there. So I was looking at the water running through the pipes and the material that's grown over time over the course of 3 months on the inside of the pipe. I was basically looking for who is there, so what microorganisms are there, how much is there, so I was quantifying the abundance of the microorganisms using old school techniques, which is plate counts, where you take a sample of water, you put it on jelly that's got nutrients in and see what grows, and using total cell counts and intact cell counts. And what that is something called a flow cytometer. It sounds super fancy. It's basically using lasers to count individual numbers of cells. So I was looking at who is there, how much is there, and what nutrients were there, like what has the potential to be there, because all of those nutrients there, like carbon at the top, that's a food source for these organisms. So what did I actually find? So on the left at the bottom there, you can see the flow cytometer, so that's the laser one. On the bottom right hand side, you can see the plate count, so that's old school, you might have seen them in school maybe. And what I actually found was there on the surface water site with both of these different techniques, surface water values were super, super high all the time, whether they had chemicals in, whether they didn't have chemicals in, whatever we did, surface water had loads of microorganisms. Conversely, groundwater, again, deep within the ground, normally generally good quality water, really low, everything. Even when we weren't using chemicals, it was still lower than anything we ever found under any experimental conditions at the surface water site. So we've got there in the blue, those are all the samples that were using lasers, like next generation, sort of really techie equipment. And on the right hand side, you've got the basic measurements. So both of those there showed that groundwater was good, surface water was bad. So what does that actually mean? It's actually really exciting stuff. It means that it doesn't matter whether we use chemicals or not, if that makes sense. The groundwater site had really great quality water, so the chemicals weren't doing all that much to improve it. So when we got rid of those chemicals, nothing really happened. It was still really good quality water. The same wasn't really found at the surface water site. It did deteriorate quite a bit when we got rid of the chemicals. But at the groundwater site, it was possible. So I found that there are sites, there are locations in the UK where this chemical-free water is a possibility for us in future. So a summary of my research today, how can we prepare for future challenges? By doing future work. Why research chemical-free water? Because chemicals can have unintended consequences. And is chemical-free water possible in the UK? It is possible, but we need to start preparing now, and that doesn't necessarily mean it's possible everywhere. So thank you very much for listening to my presentation this evening. I really apologise for the technical difficulties I had at the beginning, but thanks so much for bearing with me. Thanks very much.